Well, hi there, Nick here, M0NTV, and welcome back to my shack and to another homebrew video. And really what I want to do today is just to tie some loose ends up around this whole business of mixers and modulators that we've been thinking about. So hopefully it's going to be a shorter video and little bits and pieces. So thank you to everybody that's watched the previous videos and has made comments and asked questions and the rest of it. It's really good. It certainly provoked a lively discussion, shall we say, on the GQRP Club reflector, and provoked all kinds of different responses from the people on kind of one extreme who said, well, actually, you know, just forward voltage matching your diodes is not enough. You know, you've got to match their capacitance, or you've got to match some of the other parameters as well. To the other extreme of people that said, why bother? You know? And actually, of the why bother people, they fall into two categories actually. So I mean, all right, yeah, there was the bloke that said, you know, why bother, because I could just go and buy one. But I mean, yeah, I mean, why bother build a radio? I could just go and buy one. I mean, that's kind of the whole point of homebrew, right? You know, I know I'm preaching to the choir here, but it's you know, I do it because I can, because I choose to, because I want to, because I want to understand how it works. Because if not, it's just another little black box that I don't know, you know, what's going on. So but moving on to the other people, there were some folks that said, well, why bother? Because does it actually make a difference in the end to your mixer? Now that is a fair question to ask. Does matching the diodes actually make a difference? To be honest, I'd kind of, you know, I'd taken it as read that actually you should match your diodes, you know. And every mixer I've made, I've at least tried to match. I mean, all right, probably some of them will match with the diode function on the multimeter, but I tried to do something. But what if you didn't? You know, so we're going to come to that, because I think that's an important one. We're going to come to that. But first of all, I just want to bring you up to date with some of the actual diode matching with the adjustable constant current source that I talked about in the last video, on some a real batch of diodes, and how well it actually performed. So were the measurements I made with this thing any good? Okay, well, let's find out. So I've been busy with my adjustable constant current source and testing that big pack that you saw in the last video of 100 1N5711 Schottky diodes, and this is the result. So, in true Charlie Morris style, two big bits of paper, and all those numbers are the forward voltage drops of all those diodes. And I tested a few first to get an idea of the kind of range, which was in the 0.75 kind of range. So then I went a bit lower, and turns out actually I could have gone a little bit lower. There's a few at the end there that didn't fit on anywhere, but that's fine. And got busy doing it. Now you have to leave them for a few seconds, I found, when you're measuring them, just because of the temperature coefficient of these diodes. In other words, when they heat up, the forward voltage drop increases, and when they cool, it decreases. And so when I'm picking them up with my clammy fingers, transferring heat into them, and then I put them on the clips there on the binding posts, and of course then so that will conduct the heat away, and so they'll cool. So
the first few seconds you'll see that the voltage will, generally speaking, will drop as the diode cools, but then very quickly I found it stabilized, and you could easily see what the true value was. And so then you start collecting them. So, and as you'll see, I've got a nice collection actually of quite a few of them that I'm going to be able to pair them up into diode rings. But of course the question now remains is, how good is it? I mean, how accurate is this little device that I built and encourage you to build? Well, I'm going to show you now precisely how accurate it is.
Now, one person who commented said, well, Nick, really what you want to do if you're going to test diodes is to get yourself a DCA 75 Pro. Well, actually, if you were paying attention in the last video, you'll know I've already got one, right? Because that's how I produced all those nice diode IV curves that I showed you. Now, he's right. It's a cracking piece of kit. I've only had this one, not even a year, I think, but it is really good. So, I mean, it'll analyse all kinds of semiconductors and give you all kinds of information. The best thing is you can actually plug it into your computer and get all this stuff up on the screen then and do screen grabs and everything. So it is really good. But actually, in the spirit of homebrew, you know, this thing costs at least £140. This thing costs hardly anything, right? So I was trying to build something that was cheaper and easier to do so that people didn't have to go off and spend loads of money if they didn't want to, right? But would still give us good results. So what I've ended up doing is I've used this to test the results of this, right? And that's been very instructive. So what you're going to see now are some of the IV curves that I did using this to see whether this really does match your diode sufficiently or not. So what I did was I selected 6, first of all, random diodes, and actually they're not all that random actually, because I went out my way to pick them from a range of different forward voltage drops. So, and you'll see here that they're color coded at the top, so each diode has its own color, and they range from a forward voltage drop of 0.705 through to 0.755. So that's a 50 millivolt range, so quite big. And you'll see here at, you know, as the diode's just switching on, they look pretty similar. They're all on top of each other, and gradually as the forward voltage goes up and the current is increased, they start to kind of spread out until you get to 10 milliamps, and you'll see that actually they're not very matched at all at 10 milliamps. So now I wanted you to see this just because this is what unmatched diodes look like on this IV graph. So now what I then did was I went to my 2 big sheets of paper that I showed you a moment ago, and I found the diodes that were in the little box labelled 0.757. And there were 6 of them, which is why I've shown you 6 random ones here. And so I tested on the DCA Pro those 6 diodes that were matched by my constant current source, and this is what I saw. Now look at that. Now you'll see again at the top there are 6 diodes. They've all got their own colour, but the only one you can see on the chart is this light blue because it's the last one, and that's because these are all matched, and those traces are laying just flat one on top of the other, and you'll see they're matched throughout the entire IV curve right up to, well, beyond 11 milliamps, and we were testing them, of course, with the constant current source at 10. So folks, you know, it really doesn't get much better than that, I think, when it comes to the business of forward voltage matching your diodes. That little circuit that I built seems to do the trick. Just so in case you're in any doubt, from those 100 diodes that I tested, I ended up, I think, with 12 or 13 groups of 4. And of course I'm going to put them in groups of 4 because they're all going to go into diode rings sooner or later. So of that group of 13 groups of 4, I tested every one, and I can tell you every single chart looked like the one you're looking at now. Every single one was exactly like that. So, you know, I'm really pleased with that. So very pleased. So I have confidence now that when it comes to matching my diodes in the future, I can use that little adjustable constant current circuit and know that it's actually doing the job, and doing the job very well. Well, that was really encouraging. So I was chuffed with that. So then I turned my attention to this other question about, well, that's all fine, but, you know, does it actually make a difference at the end of the day? I mean, why bother matching your diodes if it doesn't, you know? And so I decided I'd try and put it to the test. So I did the unthinkable, really. I built, as carefully as I could, a double balanced diode ring mixer with the worst matched diodes I could possibly find, right? So they're all those same 1N5711s, but with the biggest gaps of forward voltage that I could possibly find. And here it is. So I have built my double balanced diode ring mixer, and actually I built it in a case that had that other commercial mixer in, which I yanked out and just put it in here on a temporary basis, just because I could use all the RF connections that were there. So here it is. Now I've wound the transformers as carefully as I can, but the diode ring, if I zoom in on here, and it won't look anything special or anything different, but that diode ring is using 4 diodes that are deliberately not matched. Okay, so I went out my way to get 4 of them with very different forward voltage drops, just to see how that would make a difference. So what we're going to do is we're going to test this thing now and see what it looks like. So I tested the diode ring mixer with my spectrum analyzer, and what you're seeing here are 2 screen grabs. So I did 2 different tests here. The first one at the top is using it as a balanced modulator, and so putting in a 1 kilohertz audio tone and seeing what kind of carrier suppression we get. Not very much, turns out. I'm not surprised at that, and if you've seen my other videos on mixers and when I was testing them before, you'll see that actually no mixer on its own, even the expensive commercial ones, in my humble opinion, seem to work very well as a modulator on their own. You need to do something else with them, and in my case that was adding the W7EL Roy Llewellyn Audio Diplexer to it, which made a huge difference. And I'll put a link in the video description to that video. It's where I was building a direct conversion receiver, and so it might not be completely obvious. So I'll put a link to that because that's certainly worth watching, because that's a great little thing. Very few components, but makes a huge difference. And then the bottom screen grab is I tested it more as a conventional kind of mixer, and I was thinking again, imagining we were on transmit, but viewing this mixer as the second mixer on transmit. So in other words, I was putting in a signal, if you look here, down here, M2, Mark II, at 13 megahertz. So that's my IF signal. So we imagine that's the signal coming through the IF stage. And then I was running my local oscillator, which will be M3 at 34 megahertz, and that was producing these sidebands, the difference and the sum frequencies, and I was just interested in the difference frequency, which is, well, 21 megahertz, so the 15 meter band. And you'll see here that we get more. We get about just over 30 dB of local oscillator attenuation there, so that's better, about 10 dB better than this one here. But the real test, of course, and bear in mind, I didn't expect this to be great because, you know, this was the badly matched diodes. The real test would be to compare this now with well-matched diodes. So what I did is I ripped out that diode ring and I replaced it with an identical diode ring, only this time I used well-matched diodes with the adjustable constant current source, and then tested with the DCA 75 Pro. So they're matched within a millivolt. And this is what I found. So you're seeing on the left hand column those same charts I've just shown you. On the right hand side are the screen grabs for the well-matched diodes. And I mean, spot the difference, really. I mean, there is a difference, but it's not that great. And I was a little bit shocked, actually, because if you compare the acting as the balanced modulator, the top ones, I mean, well, 5.5 dB or something. I mean, yeah, that's, you know, not insignificant, but it's not huge. And if you compare the bottom traces, then there's even less difference if we compare the M3 marker here. So this is the local oscillator here. So we were getting 47, minus 47, getting minus 49.6. Now, there's a little bit more loss in the well-matched one as well, interestingly. Yeah. I was a bit deflated, really. Yeah, I wish I could have shown you these charts showing that there was made such a huge difference. But so it makes a difference, but not massive. And in full disclosure, actually, that when I swapped the diode rings over and I put the well-matched ones in, that second diode ring I didn't build very well. I just kind of threw the diodes in fairly quickly and put it in. And you know, that performed worse than the poorly matched ones. It was worse. The figures were worse. And I'm sure that's not because, you know, diode rings don't want to see matched diodes. It's because I didn't build it very carefully. And actually, my takeaway from this, I think, is not that matching your diodes is a waste of time, because I think, you know, anything you can do to build it more carefully and better is a good thing, right? and it doesn't take all that long. So I mean, I'm still going to match my diodes, but what I have taken away is the fact that you can use really badly matched diodes, but if you build that diode ring carefully, it can still perform better than a poorly made diode ring with well matched diodes, right? So actually the construction and things like whether it's symmetrical, whether the leads of the diode are the same length, there's all kinds of little things you can do, and there aren't really that many components in a diode ring double balanced mixer. So really it's worth taking your time, I think, and building it as best you can. And the other good news, I suppose, from all of this is that by the wonders of a couple of transformers and these 4 diodes, even if you use really badly matched ones, if you haven't got the time or the ability to match them, it stands a pretty good chance of working. And as one of my commentators in the video pointed out, with many of these things, you are able, with the exception of that balanced modulator, which I've already talked about, the RF Diplexer, but with many of the others, you can filter them out. I do note down here, actually, that the main difference between this one and this one, you notice these little spurs. Now, we've got these 3 tiny little spurs down here, which are these. But these bigger ones are here as well. So, it is what it is. But I think it'll work. But the more carefully you can build it, and that goes beyond just matching forward voltages of diodes, but actually construct it carefully, the better it will work. Well, there you go. So now what I should say is your mileage may vary. I built at least one diode ring mixer to exactly the same design, and I found that actually if I increase the drive, the LO drive, if you're using it as a balanced modulator, you can take that carrier right down. So it's worth having a play around with those things. The other thing as well is that you can use a little 100 ohm trim pot on the if you look at the schematic on the left hand transformer. Instead of just going to ground, you go to this trim pot, and you can use that. Some people have used that. I've put it in some of my mixers before to kind of balance out and get the carrier down as well. So check out my friend Pete Juliano's brilliant stuff on that, and so he's a big advocate for that. That's a very useful thing to do. And I think that's about it. I don't know about you, I'm just about all mixed up now. So I think I'm happy with those mixer modulators now, and they're going to suit me just fine. And I'm going to turn my attention, I think, now to the IF stages. So, and the radio's coming together. So, but that's for next time. Thank you ever so much for watching. If you've got any questions or comments, as always, stick them down below. Please subscribe if you haven't already. And I will see you on the next video. Look after yourselves. Cheers, 73.